Hello, everyone. So I'm Pete Moyer. I'm a consulting engineer with Nokia Ion, and we have
Muhammad Durrani. I own global network architecture team at Equinix, and my team is responsible to design metro, national, and regional backbone.
So we're going to share this talk in two pieces. It's about segment routing for DCI. So here's the agenda. So I'm going to go first. I'm going to give a background of segment routing, keep that really short because you guys kind of get that. Talk a little bit about what the technology choices were and kind of why. And then I'll hand it over to Muhammad. We'll get to the more interesting stuff, which is the actual use cases on how they're using the technology inside Equinix. So I got one slide on the background. I think you guys get this. There was a talk yesterday as well. I copied some of these directly from the IETF. So, segment routing is a source routing paradigm without the need for per path state. So the beauty of segment routing is there's no state in the transit nodes, right? So you basically build a label stack. I'm using the word label. That stack could be an IPv6 address, as it says there. It could be MPLS or IPv6 in the data plane. In this use case, we're actually using MPLS, also called a SID list, segment ID list. So that's populated at the head-end node, and then the transit nodes just pop. Pretty simple. So segment routing for DCI. So DCI could be fairly simple, data center interconnect. If you have a couple data centers, the topology is probably pretty basic. This use case assumes a fairly diverse topology with many data centers, upwards of maybe a dozen or so. So there's a lot of data centers. It's not a simple topology. That's one point. The other point is the services and applications that Muhammad's going to talk about later. Actually, some of those require traffic engineering for SLA. So there is a need for traffic engineering. And then the third part, as you see at the bottom, they wanted TE, but they didn't really want the added complexity of managing something like RSVP-TE. There's no RSVP-TE today in their network. They have LDP. So they wanted the traffic engineering capability without the overhead. And basically that kind of drove it to segment routing and traffic engineering. So some specifics. So traffic engineering is very well supported in segment routing. All the stuff that you've come to like and know within RSVP is in segment routing. In this case, what's different is the IGP floods that information, well, kind of like the previous RSVP where the IGP floods. So the IGPs have been extended yet again to support things like node SID and adjacency SID. So the IGP floods. A traffic engineering database is built either at the head-end node in a distributed model or in the controller. We'll talk about the controller in a bit. The path is determined. The label stack is created. Again, I'm using the word label stack because we're using MPLS and not IPv6 in the data plane, and that's populated on the head-end router. Pretty basic. So that gives you some of the traffic engineering capabilities. Now, for fast reroute, which is another big use case for RSVP, that's also a requirement. So there's been some IP fast reroute work going on for quite a while. I mentioned LFA here. In this case, they're actually going to use TI LFA, topology independent LFA. It gives you 100% topology coverage with predetermined post-convergence paths. So there's no loops, and it gives you 50 milliseconds. So that's another advantage that you get with segment routing. Now about the control plane, I talked about the IGP kind of being the control plane, but if you really want full advantage of traffic engineering in the segment routed network, obviously you need a controller. I'm a fan of controllers. Controllers are good. Obviously you want to crawl, walk, run, so you don't want to try to cram every knob in RSVP up into the controller. Kind of take it slow, but if you really want to take advantage of TE, particularly the global view of the network and the visibility you can get in a controller, there's huge advantages there. So what about the data plane, as I mentioned? So this will be SR-MPLS. MPLS has been around for decades. Actually, interesting enough, my first exposure to MPLS was at NANOG here in Denver in 1999. So that's like 20 years ago. So it's been around for a long time. So operators fully understand MPLS, just like IGPs and BGP. So that was a fairly easy choice. Now, obviously there's an option of IPv6, also known as SRv6. It's capable, it's interoperable, it's functional. There are a little, pros and cons between MPLS or IPv6, but the main decision factor was They have LDP in their network today. They're familiar with MPLS, so it just makes sense to stick with MPLS in the data plane. Plus, there's some inner working that needs to be happened during the migration. So what about the data center overlay? So this is really about DCI, but what's interesting about this use case is the segment routing head-end node is actually at the leaf inside the data center. So it's MPLS inside the data center. So once you talk about that, you kind of need to talk about the services that are being provided. EVPN provides L2 and L3 with a common control plane. Everyone loves BGP. It leverages BGP. Highly scalable, and it's kind of interesting that BGP continues to be extended over and over again over time. Within EVPN, there's many route types. I won't go into a lot of detail, but these 4 are actually being used in these use cases. Type 1, 2, 4, and 5. Muhammad will probably talk about these as well. Type 2 is kind of the anchor for EVPN that's binding the MAC with the IP address, right? Because MAC addresses are advertised in BGP in EVPN. There's things like Type 5, IP prefix advertisement, if you just want to do inter-subnet routing, and then 1 and 4 for things like multi-homing and fast convergence. Now, when you talk about EVPN inside the data center, the next question that typically comes up is, well, what about VXLAN? Because EVPN and VXLAN seem to be kind of tied together when you have a conversation about data centers. So that's a choice, right? They could have chose EVPN with VXLAN data plane. VXLAN is maturing. It's been around, I think, 2012-ish, versus MPLS. It's been around, again, a couple decades. Not yet reached feature parity, so it's close, but there's some gaps. It's growing, it's maturing. It is multi-vendor, it is interoperable, it is deployed, but you really can't say it's widely deployed. I mean, you can't point at a dozen networks and say they're doing VXLAN. Maybe inside the data center, but not so much inter-data center. So it just makes kind of a lot of sense to just stick with MPLS. So why EVPN? I kind of covered that in the previous slide. MPLS in the data center, the next question that typically comes up is, well, how do you support it in the gear, right, at the leaf? Typically, the leafs are kind of bare bones, kind of dumb. In this case, they're actually leveraging what they're calling a Smart Edge initiative. So it's fully L3 at the leaf, which is fairly common in large data centers already. In this case, the leaf is actually a fairly capable device known as a router. So it's a fully capable MPLS BGP router at the leaf, and that is your head end. That's your segment routing endpoint. Back to VXLAN. So VXLAN is kind of needed to support NFE. In this use case, the CE device is actually not a multi-tenant server like a typical data center, right? Equinix is an IXP. So that CE device is actually another router or potentially a switch. So you really don't need virtualization there. However, if they wanted to support multi-tenant servers in their data center, they could do that and then run VXLAN from that server to the leaf node. So you have VXLAN to give you that multi-tenancy truly at the customer edge. And then on the leaf node, which basically functions as a gateway, you kind of stitch the VXLAN tunnel into segment routing MPLS. So you have that stitching capability in the device as well. Again, that's a fully capable MPLS router. So to wrap this up, kick it over to Muhammad to cover the more interesting stuff. So I have a pretty long acronym there, but that's basically what the kind of use case resulted down to. It's EVPN over segment routing using traffic engineering with MPLS in the data plane. So it's pretty much a mouthful, but yeah, that's the basis for the use cases. And with that,
this is the one.
yeah.
Okay, so why segment routing? When we started our journey in Equinix 2 years ago, Equinix inherently have services which are metro-based service architecture. Every metro have services, and they have silo fabrics for every service. It was a good design because your blast radius would be, if something happens to a specific service, it contained within that service. But there are pros and cons. It might be a higher capex cost, right? Because you are spending 4 times, but any service you build a new fabric, right? So initiative that we took as a company is, can we consolidate and reduce the capex and opex price, right? So big task given to us is reduce the price to lower compared to what we are spending, and that was the initial goal for us. Second goal was architecture optimization. Make sure architecture is simple, is single technology, low number of vendors, and it's easy to debug, easy to provision services, and it's coherent across all different services. Service delivery time was one of the major attribute given to us. If you're using different technologies, different vendors, amount of work you have to do in an orchestration layer is increased significantly, right? So if you consolidate service provisioning to a certain technologies, it reduces your development time. So that was one of the goal for this. And the primary drive to do a consolidation was readiness for 5G. 5G is driving significant investment on an infrastructure. It comes up with various requirements of network slicing, and it's very tough to achieve it with traffic engineering. So why EVPN and why segment routing? EVPN, currently we're running network with MPPGP, and then you have to run EVPN for L2 services. And what if we just select EVPN? It can give you a variety of services. It gives you ELAN, E-line, E3, L3 VPN, DCI, everything in one. Good protocol, stabilize, test it, work fine. Second one is it supports both data planes, VXLAN and MPLS, right? Great technology to try out, works fine. So why segment routing? Lower CapEx. Inherent problem with traffic engineering is, I lived with traffic engineering for 12 years. It maintains soft states in every hop in the router. You create traffic engineering from a head end to your midpoint, you need to maintain soft states of the traffic engineering tunnel. It imposes more restrictions on the memory. You need to process packet per second, you need more memory, more CPU, and then there's a RSVP hellos going back and forth. You need heavy routers. You cannot go for merchant silicon or white label in the core. So the core concept of dumb core is pretty much complicated to implement with traffic engineering as your protocol. Another great advantage that segment routing gives you is traffic engineering is circuit optimized, meaning if you have an ECMP path in your network, you have to create one traffic engineering tunnel per path. So if you have 4 ECMP paths, you need 4 traffic engineering tunnel and map your package to 4 tunnels. Segment routing being packet optimized, you just create one service policy, and that service policy will take care of ECMP. So you embrace IP ECMP significantly with segment routing by just creating one service policy compared to 4 service policy. So your service creation of 4 versus 1, reducing the time, and you can use entire bandwidth available in your core network. Biggest advantage. Lower OpEx is the tooling required to monitor my RSVP traffic engineering, then my ISIS layer is significantly reduced, because segment routing eliminates the need to enable any protocol other than just IGP. So in an ISIS or BGP, you enable traffic segment routing extension, and voila. You don't need any RSVP and all. So provisioning services, debugging problems in the network, and then orchestration of services becomes very easy. Now, advanced value-added service offering that segment routing brings in is to implement class of service-based traffic engineering. If you need to provide critical, medium, low, these type of service to the customer, you need one traffic engineering tunnel per class of service. And again, when you create one tunnel, it creates soft states, right? So if you have 100 customers, you have 100 tunnels, 100 soft states in the router. With segment routing, it's stateless service policies. You don't have to create soft state on the transit router. It's only head end needs to create a policy, and it's stateless. Big advantage with SD-WAN emerging. If you use PCE controllers, you can integrate with SD-WAN controllers and embrace service policy notions to even select which path in the service provider network you can take for your enterprise customer. So you create service policies. One service policy will be low latency service policy. One service policy would be encrypted service policy. Other service policy would be best ever policies. You'll get just one label. And when your enterprise customer asks for this service, you just give them the label. It says, push me this label. You come to my network. I'll take you to the path you want, right? So with traffic engineering, it's tough to do it. There's a concept of IGP shortcuts. You do it, but you don't have a control because your IGP shortcut goes in an IGP table, and you don't have no control to take the traffic to IGP shortcut. So it gives you fine-grained controller how you street the traffic through your network. The final one is 5G rollout. I previously mentioned that 5G rollout driving significant investment in network infrastructure. And sooner or later, in a year or two, you will start getting requirements from your customer that I want a network slice for low latency, network slice for encrypted path, network slice for high available path, right? So easily achievable with segment routing with low overheads. So now I'll give you a deep dive on what are the various use cases that we implemented in Equinix and are about to implement. So use case one is low speed Metro Connect services. So currently we provide 10 gig and 100 gig services on optical cross connects. It's pretty expensive. We are trying to move because 10 gig is a new 1 gig, right? So we are moving all these 10 gig services to low speed Metro Connect to bring the cost down, right? In optical world, there's a notion of protected path. So you have a primary path. If path goes down, you need to do a protection on the path. And to have that type of control on your packet network, you need some traffic engineering policies. Which, if we go, so that's one of the complications on this. So the two type of service we were providing to our customer, one is dual diverse, and other one is single protected. When I say dual diverse is, you have two disjoint path, east and west. There's no fate sharing to it. And second one is single protected. You have one path, but it's protected. Any infrastructure links goes down, your service remains up. So two type of services we need to provide to our customer. And we were using link coloring to tag east and west, and service policies on traffic on segment routing, but traffic engineering tunnels for traffic engineering. So we run two proof of concepts, parallel running with each other. Then there was a requirement that since this optical link is a layer 1, any L2BPDU customer is transforming should be seen on the other link. It's a garbage in, garbage out type of technology, right? So any MACsec, even overlay MACsec customer running on CE routers should be transparently flood through this L2 circuits. And there will be 50 millisecond convergence that customer wants in the network. The path has to be eCMP for us, right? Because we have enough bandwidth in the network, and I want to make sure I use every bit in my network, right? And I don't want to do too much to do that, right? So let's see how traffic engineering and segment routing fares out. So left-hand side is segment routing, right-hand side is traffic engineering. From a deployment point of view, looks pretty similar, but one inherent advantage I'm going to mention here for segment routing is, if you see my DC2 on the left-hand side, it becomes a core routers. My service instantiation happened on DC1 R1 routers, and it's terminating on R7 router. I created a service policy on R1, and it creates a source routing header to go over my red links, which is R1, R3, R4, and R7 at the top, which is green, sorry, and at the bottom is my another policy. So I have two disjoint paths. All I did on segment routing is create a source routing header on R1. It creates a source routing header, give it to R3, R3 look into the label, forward it to R4, and then R7, done. There's no need to create a traffic engineering tunnel. On the other hand, on the right-hand side, on the traffic engineering, I had to create a tunnel on R1. It will generate a path message on R3, R3 will send a path message on R4, R4 will send a path message to R7, and then once the bandwidth is reserved, R7 will send a reservation message back from R7 to R4, then R3, then R1, and my tunnel will be established. So my R3 and R4 are not dumb core. They need to understand traffic engineering, they need to maintain the soft state, and the goal of low operations and CapEx costs, I cannot achieve with traffic engineering. So in segment routing, what we did, we took out the customs ASICs, and we pushed merchant silicon boxes to bring the cost down for the overall solution. So R3, R4, and R5 and R6 are my are my merchant silicon. R1 and R2, R7 and R8 are my custom silicon. So the concept of dumb core is reality. It brings the cost down. Okay, so simple technology, and we achieved the goal we wanted. It's simple to do it. Use case number 2. Everybody is very familiar now with the IXPs. You do public and private pairing. So the design goals that were given to us, again, is low operation and CapEx cost. Same thing. Here, to bring the cost down, you need to have a mix of merchant and custom silicon. And if you go with the traditional MPLS traffic engineering, it's tough to put merchant silicon in the core routers. Next one, the service types that we need to offer to the customer is multilateral and bilateral public and private pairing. So they translate back to 2 services, ELAN, EVPL, for both MPLS and segment routing. Avoid layer 2 flooding. EVPN takes care of it. It does MAC routing, so both can be achieved with segment routing and traffic and MPLS, traditional MPLS, with route type 1 and 2 and 4. Service migration. So current network that we have is based on VXLAN. Even in past, we avoid going traffic engineering path to do an IXP, is because it puts lots of tax on your core routers. If you go with stateless VXLAN, it's cheap from operation point of view, easy to debug, it's easy to implement, and you don't need heavy hitter routers, so it brings your CapEx cost very low. So current implementation we have is VXLAN. So if we try to go segment routing or MPLS, you need to bring a gateway function to it, right? So again, I have so much bandwidth in my core, I want to make sure the technology I'm picking up use ECMP as a protocol, rather than with the same simple configuration, rather than throw too much of configuration and then consume ECMP. So the left-hand side you see is it's pretty much demonstrating how basic IXP works. You have a SaaS provider, it's creating public pairing, so it established after L2 extension happened, it's creating a EVP or BGP session with MLPE. Then you have enterprise A, also want to do a private public pairing. It's do BGP session with MLPE and the enterprise B as well. So there's a public pairing, normal world happen like that, and then enterprise A and B can do a private pairing with each other using a point-to-point BGP. No, on the right-hand side, you see if we bring in segment routing on whatever we have on the current network is a brownfield implementation, you need to bring in a concept of gateway routers. You bring in 2 gateway routers, and through a service model, through a controller, we create a service model. If your point A is on legacy network and point B is on segment routing network, you create a gateway function and then integrate these 2 technologies together. And we have migration planned to move our customers from a VXLAN to a segment routing, old customer from a VXLAN to a segment routing. You can run both in parallel for day 1 and then do a cut over to a segment routing. Use case number 3 is enterprise cloud exchange services. We have lots of enterprise customer in our data center. They want to consume goodness of Google Docs. They want to connect to Microsoft Azure Cloud. They want to connect to Amazon Infrastructure as a Service platform. The services translates into layer 2 VPN, L2 services, or layer 3 VPN if you want to connect to SaaS providers. And another restriction it imposes is service chaining. Lots of SaaS providers do not want to accept public IP addresses from the customer because there's fear they can get attacked if they're learning a public IP address and they're not verifying them with IRR database. So you need to do a natting to your IP address range, and they allow and they trust your IP range. So there's a service chaining needs to be done for layer 3 service providers. This is where it becomes a little tricky because in traffic engineering, you need to create 2 tunnels from point A to the service farm, then from a service farm to point B, and stitch these 2 tunnels. So service T tunnel stitching is pretty complex. With segment routing, I'll show you how we'll do it in the next diagram, is you just add a source routing header right at the edge, and it'll take you to the entire path. So one complication there. Second is class of service-based traffic engineering tunnels. On segment routing, since the policy is stateless, you don't have to maintain states at the edge routers and at the core routers. But for traffic engineering, for every COS, you need to create one tunnel. So again, scalable config, it doesn't work. So left-hand side you see is current network, which is MPLS, LDP, TE based. And if you bring in a notion of segment routing and do the integration on the brownfield, same methodology, you have to introduce a gateway routers. And through a service model, what you need to do is to stitch your legacy customers, point A if exists on your legacy fabric and point B exists on your segment routing fabric. You need to implement a gateway function, and it can stitch these two services if customer resides on either side of the fabric. On the right-hand side, if you see, I'm trying to show here if I want to do service chaining, just need to do an enterprise side. I need to just insert a SID list. SID list is telling me that go to router 200 and then take 201, get NATed, come out of 202 as a label, and get to 300. So if same thing I have to do with traffic engineering, I need to build an enterprise, a traffic engineering tunnel up to my router R3, and then somehow forward the packet to NAT, get it back, and have another tunnel from R3 to, there's a typo, sorry, R3 to the router connected to Google, and stitch these two tunnels. So chaining becomes complicated with traffic engineering inherently. The last use case is driving our 5G requirements. We are already getting requirements from customer where customer is asking a network slices. So again, low OpEx and low CapEx, that's one of the drive. Second one is the service types. Customer asking, give me, a financial customer asking, give me an encrypted slice in your network. Other customer asking, give me a low latency path through your network. Another requirement from a customer is, I need service chaining a NAT with a firewall. And the fourth type of service is, I need a high bandwidth path, but it's best effort. Give me a cheaper service, right? You can implement all of that with segment routing by just throwing a service policy which is stateless, which is the goodness. And with the traffic engineering, you need to create traffic engineering policies, but they are stateful. And to bring the price down, you need to have heavy hitter routers end-to-end in your network path, right? Second is, I talked about previously again and hampering again is your network have enough bandwidth, just use it. So for traffic engineering, you need to create multiple tunnels for every ECMP path. For segment routing, you don't need to. It inherently uses your ECMP. It's packet optimized. It's not circuit optimized. So if you see in this diagram, Enterprise A, HQ, needs to connect to Enterprise A branch A. And think of it as my encrypted path or my low latency path. I create one service policy, blue service policy, and this service policy will hit my core routers. And you see in my core router, he sees two paths to go to branch A. So it will do ECMP by itself. If on the right-hand side, I have to create two traffic engineering tunnels, one goes to one ECMP path, other goes to another ECMP path. So my service configuration reduced. I don't have to do extra efforts to do ECMP, and it's easy to debug because I don't need to do RSCP traffic engineering. I don't need to enable RSCP traffic engineering. ISIs can do the job, or BGP. So in summary, EVPN overlay in a DC combined with SRTE for DCI is technologically ready. All you need to do is put your faith in and then try to test based on your use cases. We engaged with vendors 2 years ago. We drove them to what we want. Drafts are getting written. You have to make sure you put your feedback in it and influence how they're implementing these protocols, right? We're influencing a lot. It's leveraged well-known, widely deployed protocols, BGP, MPLS. Problems are solved on RSCP already. All they need to do is to take this problem statement, try to solve it in more simpler manner. So it's another optimization of how the problem was solved in MPLS traffic engineering. Same problem can be solved easily on segment routing. Easy and simple way. Equinix UPF architecture is collapsing all multi-services into cohesive infrastructure. So now we don't have service-based architecture, we will have cohesive single architecture with distributed overlay, centralized underlay over EVPN. It reduces complexity for my operation. They don't have to deal with multiple technologies. It's one segment routing technology they have to debug. We are able to provide high customer QoE. QoS and TE for multiple services can be achieved with low CapEx. Protection and fast reroute services are maintained through TI LFA. We don't have to do fast reroute. It provides fine-grained control over service chaining, which was a complicated function to implement in the network. And we also trying to pursue our virtualization data analytics with segment routing. Any questions?
Okay, thanks a lot.